In this video, we are going to showcase the application scenarios of our Capricorn system, a multimodal sensor fusion system analyzing the scene in real time. Imagine in a factory or workshop, we have a number of machines operating simultaneously. It is important to monitor the operating status of each machine to improve security and productivity. Capricorn can detect and identify all the targets of interest in the scene and estimate their operating status based on their vibration profiles acquired using an ultra-wideband radar. In this setting, we exhaustively tested all the combinations of the on-off states of the 4 drills in the scene and can achieve a high accuracy. Similar technologies can be applied in smart home scenarios. In the second setting, Capricorn is tracking and monitoring the operating states of a few household appliances, for example, washing machines, vacuum cleaners, fans, etc. This technology can benefit household robots for home monitoring, like Amazon Astro. By making inference about the states of these household appliances, we can make them smart without instrumenting them with additional electronics. Nextly, we demonstrate how Capricorn can benefit the research of complex event detection. A complex event detection system needs to firstly understand a number of simple atomic events, then make logical reasonings to model a complicated event that spans across space and time. In this example, we show an event where a person is doing laundry. This complex activity is modeled as a finite state machine on the right-hand side, and we start with the idle states. Just now, we can see that the state transition fired and we are now in the washing state. The state transition happens because Capricorn detected that the machine's vibration mode changed from idle to washing. This is a benefit we want to emphasize that is brought by Capricorn. With vision sensors, we can only capture the interaction between human and the machine, but the machine state is invisible. By fusion of wireless sensing and vision, we can make inferences of the operating states of the washing machine and provide a wider range of possible atomic events. Here, because Capricorn detected that the vibration from washing is gone, we move on to the next state where we send a notification to the user saying the washing is done and the clothes is ready for drying. The next state is triggered by the vision sensor detecting that the person starts to interact with the washing machine. When Capricorn detects the vibration of the dryer, we move on to the next state for drying. Another alarm is sent when the drying is finished. Finally, with the person interacting with the machine again to collect the clothes, we finish a laundry cycle and move back to the state of idle. Capricorn employs ultra-wideband radar to detect vibration at different distances and then associate with corresponding objects based on the vision sensor inference results. A natural question arises that if 2 objects happen to be sitting on the same distance, we could make mistakes when extracting their vibrations. In this scene, we demonstrate that the architecture of Capricorn is scalable, and the problem mentioned above can be easily resolved by adding another view of sensors with minor revision to the code. 2 objects at the same distance, d0, will have different distances towards the second set of sensors, and their vibrations can be separated there. In this video, the ground truth is that the left drill is off and the right one is on. The left-hand side is the single-view Capricorn, where the vibration of the right drill contaminated the states of the left one because they are sitting at the same distance. But with the second view being added, the state estimation is accurate again on the right-hand side. The radio frequency components in Capricorn can not only measure the high frequencies, but also low frequency mechanical movements like human vital signals. Imagine after a mass casualty event, we send a team of robots for reconnaissance and search for survivors. In this stage setup, we use dummies to represent bodies. Conventionally, the situation awareness of intelligent system has been developed using camera and computer vision only. We can see that while the object detection and recognition system can recognize human objects, they can be easily confused or deceived by dummies. It will be difficult for such camera systems to distinguish survivors from bodies in our settings. In this work, we propose a multimodal sensor fusion method. Combining camera, LiDAR, and ultra-wideband radar, we can build a richer and more comprehensive understanding of the scene. As shown here, RF sensing and computer vision algorithms can collaborate to assist each other. The computer vision systems provide external object information such as object type, bounding boxes, and distance. Meanwhile, the RF sensors provide object internal information such as vital signals. In this case, the vital signals we are monitoring is human respiration. The ultra-wideband radar allows us to simultaneously estimate and separate the vital signals from multiple objects. In the end, we can decide that we have discovered 2 survivors in this scene, and a rescue mission could then be launched. Finally, we leverage the last scene to demonstrate the underlying technology of Capricorn in a high level. Firstly, we use a state-of-the-art YOLO model to detect all the persons in the scene. Nextly, we align the RGB frame with the LiDAR depth frame. We can then migrate the bounding boxes onto the depth channel. We estimate the distances between the sensor and each object in the scene using these bounding boxes. Our research has demonstrated the ultra-wideband radar's capability to capture and separate multiple vibrations at different distances. The depths estimated from LiDAR help us to take slices from the 2-dimensional data matrix and select the waveforms corresponding to each object. Now we can integrate all the components into a real-time system. Our system can simultaneously estimate the bounding box, type, distance, and vital signals from multiple objects in the scene. We can see that objects 1 and 3 are persons showing vital signals and thus become the survivors we are looking for.